Example 3.3 is where we first run into compound interest. And compound interest is a pretty cool thing. Now, take that with a grain of salt. This is a huge nerd telling you that. But walking through this example, we can get a sense for how powerful compound interest really is. And before we dive into the example, let's back up for just a second and talk about the difference between simple and compound interest. Now, in the previous two examples, well, really just the previous example, 3.2, we were really only looking at simple interest because we were only looking at a 1-year period. We only earned interest in our bank account for 1 period. If we start looking beyond that, we're going to start running into compound interest. All right, now simple interest is just the amount of interest paid on the original principal. So if we deposit $1,000 in our bank account, it earns 10% interest, and we let it sit there for 1 year, right? We deposit our $1,000. It earns 10% interest for 1 year, so it grows 10%. That's $100 worth of interest. At the end of that year, our bank account balance will be $1,100. That is the original $1,000 that we started with, plus the $100 in interest that the bank credited us. Now, something cool happens if we let that money sit and earn interest for another year. The bank is going to pay us interest both on the original principal of $1,000, but also on the $100 interest they credited us before. That is, now, when we want to know the balance in our account 2 years from today, we're going to take the $1,100, multiply it times 1.1. We're going to make it 10% larger, which is going to make it $110 larger. All right, now notice the amount of interest that we got credited from the end of year 1 to the end of year 2 is $110. And that is compared to the amount of interest we earned in the first year, which is just $100. So we got $10 more interest, right, on $100. So that's 10% more interest in year 2 than we received in year 1. That's because we are earning interest on interest. That is, we earned another 10% on the $100 worth of interest that they paid us in year 1, that the bank paid us in year 1. And so not only did we earn another $100 on the original principal, which is the simple interest, we earned an extra $10, which is the interest on the interest that they paid us before. And so our account balance is $1,210. Right? Now over 1 year, hey, an extra $10 doesn't seem like a big deal, right? But it becomes a really big deal over time. And let's take a look at example 3.3 to see how that works. This example says you deposit $1,000 in an account that pays 10% interest per year. You do not make any other deposits or withdrawals. What is your account balance 30 years after you make the deposit? So we start out with a timeline here, just seeing what the cash flows look like. We're going to deposit $1,000 today. We're going to earn 10% interest on it, and we're just going to let that $1,000 accumulate interest all the way out to 30 years from today. And this FV here stands for future value, where the 1,000 is our present value we started out with. After 30 years, our account balance is going to be what we call our future value. Now, earlier in the chapter, if you skipped over it, we introduced the general future value present value equation, where the future value is equal to the present value times, recognize our interest rate factor here, 1 plus r, raised to n. That's the number of compounding periods that our present value earns interest over. So in this problem, our present value is $1,000. That's what we start with. Our interest rate factor is 1 plus r, or 1 plus 10%, which becomes 1.1. And it is going to compound 30 periods, right? So we're going to raise that to the 30. So if we plug that into a calculator, we'll find out that our account balance is $17,449.40. Right? Let that sink in for a minute. We deposited $1,000 and we just forgot about it. We just left it there. That turned into $17,449.40 over the course of 30 years without us doing anything else. Right? Now, let's look at a chart to see what's actually going on there, because when we break down where that growth is coming from, it's pretty darn cool. Right, so let's look at year 1. Our beginning amount was $1,000. We started with $1,000 in the account. They're going to credit us $100 in simple interest There is no compound interest because we're not earning interest on interest yet. And so our total interest earned is $100 and our ending account balance is $1,100. So at the end of year one, we've got $1,100. This is exactly what we saw on the timeline right above here. So we're just accounting for all these different values coming together to create that ending account balance. At the end of year two, or at the beginning of year two, we're starting with that $1,100. We're going to again be credited $100 simple interest, but then we're going to earn 10% interest on that simple interest. And so we're going to get an extra $10, and our total interest over year two is $110, and our account balance at the end of year two is $1,210. Okay, so we saw that on the timeline above, nothing new there. If we go to the beginning of year three, now we're starting with that $1,210. We're going to, again, over the course of the year, be credited $100 in simple interest. But now our compound interest is on the total accumulated $200 worth of simple interest, the $100 over year one, the $100 in year two. And so we're going to earn 10% on that, which is going to be $21. So our total interest earned is $121 over the course of year three. And so our ending account balance is $1,331. This process continues, and what I want you to notice is that the simple interest we get credited every year is $100. It doesn't change. Right? Look at the accumulation of compound interest. It goes from $0 over year one to $10 over year two. If we jump to year 10, it's up to $135.79. And this is not accumulated compound interest. We earned $135.79 just in year 10 of compound interest. It's now more than the simple interest that the account was paying, and it continues to grow quickly. Like it doubles by year 16. In year 10, it was $136 roughly. By year 16, it's over $300, and it just keeps on growing. It grows faster and faster and faster. And finally, by the end of year 30, if we look at the total accumulated interest, we've got $3,000 worth of simple interest, right? That's just a sum of all the simple interest payments over 30 years. And if we look at compound interest, we were paid $13,449.40 in compound interest, right? So our total interest payment, when we add those two together, is $16,449.40, which plus our $1,000 original principal gives us that $17,449.40 that is in our account. This is what we call, compound interest is what we call an exponential function. That is, it gets larger at an increasing rate as time goes on. If we were to look at this in chart form, right, we've got a breakdown here of the original principal of $1,000. That's our darkest shaded region in these bars. And then we've got accumulated simple interest, which is the slightly less dark blue region on each of these bars. And our accumulated compound interest, which is the lightest region on top. We can see the shape of this function as we go from year one out to year 30. There, of course, is no compound interest in year one. There's only a tiny little bit at the end of year two. It's just the $10. But then it increases at an increasing rate until it just dominates everything else. That compound interest is our greatest source of income as we get later on in time. Now, you're probably thinking 30 years, $1,000. Come on, how realistic is it that I'm going to save for 30 years and it was only $1,000 to begin with? There's all kinds of reasons this doesn't make sense. It's just a stylized example. But I'll challenge you to think about this. Many of you are going to be graduating college, say 22 years old, roughly early 20s. If you were to start saving even just a few $100s when you graduate, when you start working and earning income full-time, just start putting some money away. If you were to let it earn interest for 30 years, if you start when you're 22, 30 years from then is only 52. You're not even going to be close to retirement. You could easily put in another 10, 15, maybe even 20 years worth of working and saving and earning interest. So just imagine how this compound interest can work for you over time on your retirement savings. It is a powerful, powerful force. Of course, that's also true if you're on the other side of it. So if you're borrowing on high interest credit cards or any other debt and you're paying interest over 20, 30 years instead of investing, of course that force is working the other direction in the same sort of power. All right, so that's definitely something to think about. Okay, the other thing I want to do for this example is show the financial calculator solution. And this is assuming that you have done the financial calculator setup. So if you haven't done that, go ahead and pause this video, go back and watch the financial calculator setup video so that you've got everything set correctly in your calculator, and then come back. If you haven't done that setup, you probably won't quite get the same numbers that I'm going to get. In fact, let's go to the appendix where we can actually see the financial calculator solution for example 3.3. All right, so we can see the calculator inputs here. I'm going to start out, as I always do, by clearing out the time value money register by hitting second and clear TVM, CLR TVM, which is right above the FV key. All right, and then I'm going to put my inputs on these 5 time value of money keys. And these things mimic what's in our formulas. N is the number of compounding periods. I over Y is the interest rate per year, or interest rate per period. This is what we call little r in the formulas. PV stands for, you guessed it, present value. PMT is payment. We won't actually use this until chapter 4, so we can ignore that guy for now. It's always going to be 0. And then FV is future value. Now these 5 keys are memory keys, so whatever I put on those keys stays on there until I clear it out or until I overwrite it with something else. So that's why I always clear them out before I start a new problem. All right, and then I like to work left to right and enter these values in, and they go in backwards than you might expect. If I want to enter the number 30 on the N key, I'm going to start by typing in the number 30, and then once that's on the display, I will press the N key to store it on N. When it's a stored value, we'll see the equal sign come up. We'll see however many decimal places we have it set to, and we'll see the sideways triangle above the number that tells us that it is a stored value. So we know that the number 30 is now stored on the N key. Okay? I over Y is 10. Now, unlike the formulas where we have to convert interest rates to decimals before we can do any arithmetic with them, the calculator knows that that is a percentage and it expects it in percent format. So instead of putting in 0.1 for 10%, I'm actually going to enter 10 for 10%. Okay, so same reverse process as before. I'm going to type in the number 10 first, and then press the I over Y key to store it for I over Y, and I can see my sideways triangle, decimal places, and equal sign to know that it's stored. My present value, I'm going to enter as a minus 1,000. So 1,000 plus minus key to make it negative, and then press the present value key to store it on present value. Now, why the 1,000? Our calculator needs to know the relative direction of the cash flows. That is, some cash flows are going to be outflows, they're going away from us, and then some cash flows are going to be cash inflows, they're coming into us. What we need to do with each problem is pick a perspective in the problem to track the direction of the cash flows from, and then just stay consistent within that perspective. I try to adopt the perspective from however the question is written. So in this one, for example, I am depositing $1,000 in an account. So $1,000 is coming out of my pocket and going into my bank account. So my bank account is receiving it. I'm taking it out of my pocket. It's cash outflow for me and putting it in the bank account. So I'm going to treat that as a cash outflow, a negative, right? Negative tracks cash outflows. For this one, actually for all the problems in Chapter 3, except for when we're calculating N and interest rate, it really doesn't matter if it's positive or negative. It just changes the sign that you're going to get back. We'll talk more about that as we go through the examples. Payment is 0. Payment would be a reoccurring payment that happened over and over again, and we don't have that in this problem, so I'm going to type 0. PMT, stored in the payment key. And then future value is what I want to find. So I'm going to hit Compute on the top left, CPT, and then press the FV key for the calculator to find the future value. And now when I hit Compute FV, the calculator used that present value, future value formula that we had before. It plugged it in and calculated the future value of $1,000 at 10% interest over 30 years is that same $17,449.40 that we found before. And we'll see this little asterisk here now to say that that is a calculated value as opposed to just a stored value.